Wow. All right, let's get started. So I'm sure you guys are all not actually here for the lecture, but actually here to see if we won the Kaggle competition. So let's get that out of the way to start with. So this is the results of the public leaderboard as the competition closed at 2 o'clock today, so half an hour ago. And you see some very interesting team names. I have half a mind to ask the TAs to judge the names on their creativity, but I feel like that'll set up some perverse incentives down the road when students think they can just come up with a clever name and get half the credit. But this is what the public leaderboard looks like. So this is the data set you're basically allowed to use for validation over and over and over again, or at least I think 3 times a day. But the actual winners are computed on the private leaderboard, which you did not see until the very end. And so here are the results for the private leaderboard. And the first place team was ranked 21 in the public leaderboard. So if a clever name is hard is in the room, please stand up. Yeah, let's give them a round of applause. Overfitting is real to the public leaderboard. This column indicates the difference between the private leaderboard and the public leaderboard.
I would expect it to last
All right, so with regards to turning in the report, it's due early next week. I believe it's due next Monday. We gave you a template. Please follow this template. It'll make it much easier for the TAs to grade. And as you know, most of the grade for the Kaggle competition, most of it will be in the report. And the idea is we want to see that you did a sound statistical process in designing your models, training, etc. And I think about 20% of the final grade is with respect to the performance on the leaderboards. Any questions about that aspect? The hope is that the writing the report will be fairly straightforward, right? Not a lot of thinking, just sort of a brain dump of everything you did. The template should make it all pretty streamlined. Okay. Yeah?
I'm curious, because the scorers all seem to approach this kind of, they asymptote at this threshold, is there something characteristic of the data that leads it to all, numbers all compiled up between 75 and 86%?
It's a good question. Yeah, I don't know. We try a new data set every time, so we don't thoroughly test the data set. So this isn't the same data set as last year or the previous year. Every year we get a brand new data set to keep it fresh. So I don't actually know the answer. No. I mean, people thought that maybe on various data sets that there's some asymptote from fundamental limit, and then someone comes up with some clever new thing to do, and then the performance jumps again. So I don't know. Yeah.
I think it's the back and forth. So when I tried classifying by hand, I could get roughly no better than 50%. So I think maybe like the lack of order.
Yeah, that could be an issue. If we use the order in the words, that could help. Obviously, that leads to much more complicated models, which was not the point of this project. So certainly, I think there are things we'll do. Yes. I'm sorry, I can't hear you.
Was the training data purposely?
Was the training purposely what? No. All right, let's get on with the lecture. So today we're going to look at latent factor models and non-negative matrix factorization. I'll also sprinkle in some useful matrix properties that you may or may not find useful for homework 5, but are useful in general. So just a quick recap. An orthogonal matrix, U, has satisfied the property that U transpose and U transpose U both give you the identity matrix, which implies that for any column or row of U, it is a unit vector, and any two distinct columns are orthogonal to each other, which means that their inner product or dot product is 0, right? And you can think of U as a rotation matrix, and U transpose as the reverse or inverse of that rotation, right? So, you know, if x prime equals U transpose x, we've rotated x to equal to x prime, then we can reverse that rotation by simply multiplying x prime by U. Right? Any subset of columns of U defines a subspace, right? You project x onto this k-dimensional subspace, defined by, in this case, the first k columns of U. Right? And so here's a simple example where U is this two-dimensional matrix that are defined along these two axes. So each column specifies one of these two axes, and we only look at the first column, then it projects down to a single line. The reverse projection will reconstruct the data points along the original space, but because we only use the first column, we've lost information on the orthogonal projections, on the orthogonal of this projection. Right. So the singular value decomposition decomposes your data matrix X into U sigma V transpose, or U and V are both orthogonal matrices, right? And it can be shown that the first k columns of U under the SVD gives you the subspace, k-dimensional subspace, that leaves you with the smallest residual, the smallest amount of unmodeled variation in the original feature space. Right. And SVD and PCA are, at least in this particular case, essentially equivalent to each other. PCA operates on XX transpose, which is basically gives you the feature covariance matrix of your data set, and the SVD operates on just X, right? And you can do some very simple linear algebra operations to show that the two give you essentially equivalent things. Certainly they give you the exact same U. Right? We ended the previous lecture with an exercise in the eigenfaces, right? If X was, well, here X is mean shift, as I call it, X prime. Each column of X prime is the mean shifted pixel values of a vectorized version of people's faces, in this case taken out of CS155, students, present and past. Then we can decompose it into a U transpose V, or UV transposed, where here I'm just intentionally taking the first k columns, where k is 12. And so every row of this U matrix, or U prime matrix, can be visualized as one of these eigenfaces, and the V prime gives you the 12 coefficients that can reconstruct any individual space. So this is what we looked at yesterday, last lecture. Right? There are concepts known as matrix norms. So if you can take a norm of an entire matrix, just like you can take a norm over a vector, which is what we looked at in the first week or two of class. And so the norm of a matrix, the Frobenius norm, is simply the 2 norm, right? And so the squared Frobenius norm is the standard squared 2 norm, L2 norm. And it's simply the sum of squares over every entry in the matrix. The actual norm takes the square root of that sum. We typically look at the square of the norm, so we lose the square root. And this is equivalent to the sum of the squares of the singular values. A trace norm of a matrix corresponds to the sum of the actually absolute values of the singular values, but we consider cases where the singular values are all not negative. And so these sigmas, if you compute the singular value decomposition of X, the sigma matrix is a diagonal with these little sigma values on the diagonal and zeros on the off diagonal. That's what these sigmas are. If you've taken linear algebra, this should be very, or matrix linear algebra, this should be very straightforward review. Right. Some nice properties of matrix norms. They are, for example, the matrix multiplication is commutative inside a trace, right? And so you can derive the Frobenius norm of the squared Frobenius norm in this case of a matrix as the sum of the squares of the singular values using the definition of the SVD and manipulations of matrix multiplication inside a trace operator. Oh, sorry, the trace operator, the matrix multiplication is rotationally invariant under multiplication inside the trace. You can do the same for the trace norm. It's a little bit more complicated. If you've seen this before, it's probably a review. If you haven't seen this before, you'll probably have to review these offline. Right. So we can use the Frobenius norm of a matrix as a measure of, in some sense, the magnitude or the complexity of a matrix. Right. So it's a matrix version of the L2 norm. It's useful for regularizing matrix variable models. So sometimes a model or model parameters are actually a matrix rather than a vector. And if you want to regularize them, this is one way that you can impose a regularization by using the squared Frobenius norm, which is just a straightforward matrix version of the L2 norm. Right. Okay. That's L2 norm. We also talked about L1 norm when we looked at vector valued parameters. Right. So the L1 norm was motivated by the fact that we wanted. Well, one of the motivations for L1 is that we want sparsity in the model that we learned. Right. And sparsity in this case is measured directly using the L0 norm, which is not actually a norm. But of course, this is not continuous. It's flat or discontinuous everywhere, so people use L1 as a convex relaxation of the L0 norm. Right. So the trace norm, right, which is the sum of the singular values of a matrix, can be considered as somewhat analogous to the L1 norm. So for those of you who don't know, the rank of a matrix corresponds to the number of non-zero singular values in the singular value decomposition of that matrix, right? And so if we want a matrix that is low rank, and the reasons for wanting a low rank matrix will become evident by the end of this lecture, then we want a norm that encourages low rank, right? We want to encourage as many singular values to be zero as possible. Again, the sum of the number of non-zero singular values is a flat or discontinuous function, right? So we can't actually directly optimize that during training, and so we optimize for the trace norm, which is the sum of the singular values. So you can think of this as the sort of the spectral sparsity regularizer. Right. I'm not going to go over these in detail. These are just some standard matrix inequalities. These are things that are very useful to know. Some of these may be useful for the homework. But in general, as you work on some derivations of machine learning methods with some of which involve a lot of linear algebra, these types of properties are very useful when it comes to manipulating the model. So things like Cauchy-Schwarz, arithmetic, geometric inequality, and so on and so forth. Okay. Sorry, I said this. Review. Now let's talk about latent factor models. So latent factor models, if you've taken CS156, especially if you've taken 156B, this is mostly review, right? And so the latent factor modeling problem was made famous with the so-called Netflix challenge. And in the Netflix challenge, we have this matrix of user ratings, right? So we have so here in this particular case, we're going to do a row is a user and a column is a movie. So we have M users and N movies, right? And so Y sub ij is the rating that user I gives to movie J, right? And we could think of ratings as some real value, as some number between 1 to 5, or just a number between 0 and 1. It doesn't really matter for the purposes of this discussion as long as it has some semantically consistent interpretation, right? And the goal then is to learn these latent factor models, right? So we want to approximate this matrix U by decomposing it into a UV transpose, where U is M by K, and V transpose is N by K, right? Or V is N by K, sorry. And so if we can learn this, right, then we can approximate every Y sub ij as a U transpose V, right? So in this case, right, if all we're given is this ratings matrix, right? So this is kind of the reverse of unsupervised learning in some ways, right? In that we're giving the labels, but we have no features, right? We're given the labels, but we have no features. And what we want to do is we want to learn some features that helps us model the labels, right? And so what this is a linear model, right? This is a linear model where we've learned a feature representation per movie and per user such that the prediction of how much a user likes a movie is equal to the inner product between the linear models that we learned before every user and every movie. And in the case where y is completely given to us, we have a full, completely filled-in matrix y. We can solve this using the SVD, the singular value decomposition.
So, like, I'd imagine in practice there's a lot of missing.
That's right. We'll talk about missing values in a few slides. But conceptually, before we go to missing values, this is sort of what's going on. Okay. So, one question is, okay, do these does this V make any sense, right? Or does U make any sense, right? And so what people have done in the past is they can, visualize U and V. One way to do that is to take a bunch of movies, look at their V, and maybe look at the first two, the two most dominant directions of variation, and then simply plot them on a 2D surface, right? And so you get something that looks like this, right? So this is from one of the original papers that studied the Netflix challenge. And so on this two-dimensional projection of the V, right? So you got movies like Braveheart and Lethal Weapon. I feel like I'm dating myself. I'm not even sure if you guys know what these movies are. Dumb and Dumber, Independence Day. And so, if you just look at this plot of movies and where they lie in this 2D projection, then you can start making an interpretation that, okay, maybe, along this axis, these are movies, at least under some stereotypical assumptions, more geared towards males versus females, or serious versus escapist, right? As this is one way to say, okay, actually these feature representations that does make sense. These directions of variability captured by the V's, right? That's what the SVD gives you, correspond to sort of statistically concentrated concepts in how we think about movies. And you'll be doing something like this, by the way, for a mini project too. Yes?
Is it another Kaggle?
No, it's a visualization project. It's going to be a lot easier. I remember last year, the students kept asking me if there was some trick question with the mini project, because it was by far the easiest of the 9 assignments. And no, it's the easiest. One of the assignments has to be the easiest. Any other questions on this? Okay, so as was pointed out, the actual Netflix problem has a lot of missing values. Right? In practice, you can't really expect this entire matrix to be filled in. So a lot of the entries in this matrix are missing, right? And yet we still want to learn this U and V, right? So and in this case, we're going to call these U and V's the latent factors that we want to learn from this matrix with missing values in it. So this is the actual Netflix challenge. The actual Netflix challenge gets more complicated, but this is sort of the core of it, right? If we were to simplify it to its core element. Right. So the Netflix challenge is also known as collaborative filtering. That's the formal name of the Netflix challenge, the problem definition. So you have M users and N items, right? A small subset of user item pairs have ratings, so that's the Y matrix. But most of the Y matrix is missing, right? And so this is applicable to any user item rating problem, right? Amazon, Pandora, anything, right? And the goal is to learn a U and V, the goal is to learn a model, right, that can predict the missing values. And in practice, that's typically a latent factor model. So here's the latent factor modeling formulation. So we only have labels. We have no features. All right, so the training data looks like this, right, for some subset of Yij, not all Yij. Right? And we want to learn a latent representation. So we don't have a representation given to us. We want to infer one. That's why it's called latent. Right? We want to infer a latent representation over users and movies such that we minimize this learning objective. Right? And so this learning objective, so the right-hand side should be pretty self-explanatory. It's the squared reconstruction error of the ratings that we do have. Right? So it's regression. In this particular case, the loss function is squared error for regression. It doesn't have to be. There are certain types of latent factor models that do classification, where this could be some sort of classification loss. But here, for simplicity, we'll just stick with regression because it's the simplest loss function, right? And then here we get the regularizer, the matrix regularizers, right? We want to regularize the squared Frobenius norm of U and V, which just basically means we want to regularize the L2 norm, right, of these parameters of our model, right? Any questions on this? Yes?
Any reason for Frobenius norm as opposed to trace norm?
That explanation will come in the next slide, yes. So there's a couple of reasons. So I should say there's, let's suppose we had the V's, right? Let's suppose someone gave us the feature vectors of the movies, right? In that case, the V's are fixed, so this part goes away. Right? The V's are fixed, and then then we're just doing linear regression, right? In which case we want to regularize by the square norm as a standard thing to do. Conversely, if we had features describing users, like their age, whatever, gender, whatever, then these are known, and then we want to learn the model so we can actually flip the problem around. We want to learn a model per movie, right? Where the users are features, right? In which case this is fixed. This goes away, and now we're doing linear regression on parameters of the movies. But of course, here we're doing both simultaneously. Right. So there is actually a connection to the trace norm, right? So suppose that we consider all possible U and V that achieve perfect reconstruction, right? And then we want to find the U and V that have the lowest complexity, right? So it turns out that the trace norm of Y, so here you imagine the trace norm of Y, right, is equal to the U and V with lowest sum of squared Frobenius norms. So by finding the U and V that minimizes this this objective, we're finding we're recovering a Y that has minimal trace norm. Where Y equals UV transposed. The proof in one direction is pretty straightforward, if tedious. It's just an application of it's just some applications of the inequalities and the trace norm operators that we talked about before, and the definition of the SVD, right? There was something else I wanted to say on this slide. I forget what it was. Yeah, let's move on. Okay. So, so this is our learning objective, right? And you can relate this now using what we talked about on the previous slide. You can relate this objective to this objective, right? We want to find a W. We want to find a matrix W that approximates the entries of Y that we have as well as possible, but it minimizes the trace norm of W, right? These two problems are very closely related, and they are equivalent when the rank of U and V is equal to the rank of W. So you might wonder, why do we care about ranks here, right? Well, recall that in the singular value decomposition, right? If the matrix that you learned ended up being rank 2, then there are only two U's. Only two columns of U matter, because the other columns are zeroed out, right, by the singular values, right? And so if the matrix that best fitted the data was actually rank 2, you only needed to visualize 2 dimensions. You only needed to learn a 2-dimensional model of the users and movies to explain the data well, right? And so it's a form of regularization where we want to learn like a lowest dimensional possible representation in order to explain the data. And that is captured by the trace norm. And it turned out that, you know, if the trace norm minimizes the rank of this reconstruction, right, that we're imputing, and that is basically equivalent to this formulation when both of them agree on the rank as in the minimal solution. And of course, this formulation is much more convenient to work with mathematically and in optimization, and that is why people prefer this particular formulation up here. Any questions on this? Okay. So as I mentioned before, there's a symmetry between users and movies, right? If we knew V, right, then this is simply a linear regression to learn U. If we knew U, this is simply a linear regression to learn V, right? We just treat the other one as known features, right? And the goal is to simply learn both simultaneously. Right? This problem can be treated sort of symmetrically either way, as feature learning / model learning for users and movies, or movies and users. Okay, so let's talk a little bit about optimization, right? So how do we actually solve this optimization problem, right? So we, this summation, this is one way that people write it, right? You sum over all possible ij, and then you simply mask out the ones that don't have observations. This is not the only way to write it. They're all sort of equivalent. It often depends on, you know, the software you're using and what kind of inputs that they take in, right? There's basically 2 ways to optimize, right? Well, there's a little more than 2, but we're going to talk about 2. And they're both sort of a form of alternating optimization. One is a very explicit one where you hold U fixed and you solve V to completion to optimality under a fixed U, and then you hold V fixed and solve U to optimality under a fixed V, and you alternate. And the other, of course, is just gradient descent, or stochastic gradient descent. So here is this the gradient calculation. Here I'm using the notation where we have a mask. You don't need to use this notation. And so here I'm just showing the gradient for U, holding V fixed, right? So it's just straightforward least squares, the gradient for least squares that you've implemented already, basically, right? For homework 1. Right. And then, as you probably most of you know by now, this actually has a closed form formula. Oops. Any questions on this? Okay. So, there's a few different ways to sort of do gradient descent. So one is, if you pick, an entry like Yij, we can update the parameters of Ui and Vj, right? We could do stochastic gradient descent on Ui and Vj, or we can only do stochastic gradient descent on one of the 2, right? Just Ui or just Vj. And of course, if you mini-batch it, you mini-batch a small subset of Yij's, and then you do stochastic gradient descent on that mini-batch. Yes.
But a single data point means a single like existing entry in the big Y.
Yeah, so the data set is typically in the form of the rating, comma, the user ID, comma, the movie ID. Right? Yeah, that's what the data set typically looks like. And so you get a single one of, so if you do stochastic gradient descent, you get a single one of those. And then you have to choose what to optimize. One option is to optimize for all the parameters that are relevant to that data point, which is U, I, and VJ. Another option is simply just to choose one or the other at random. Right? And with the mini batch, you get a batch of rating, comma, user ID, comma, movie ID examples. The other option is to do alternating optimization, which is typically faster if the data set is smaller. Can be quite expensive if the data set is huge. You basically choose one UI or VJ somehow, let's say at random, and then you loop through all the data, right? That interacts in this case with UI, and then you solve for the closed form solution for that UI, assuming all other variables are fixed. This is typically faster if the data set is relatively small. But this looping through the data can be very expensive for very, very large data sets. And in practice, people don't do this for real data sets. Yes?
So I think that the original factorization problem is non-convex.
That's right.
Are either of these algorithms guaranteed to approach an optimum, or
none of them are guaranteed to converge to the global optimum. So if you restart with a random initialization, you'll get different answers. Right, so I already said this. Multi-line optimization is much faster in terms of number of iterations, requires inverting a matrix, and looping through all the data. Gradient descent is faster for stream if you need to stream, if the data is too big, or if the dimensionality is very high. Okay, so here's another visualization from the paper. So here, the authors centered the visualization around the movie Wizard of Oz. And then they plotted all the movies, a bunch of movies sort of in terms of where they were in relation to Wizard of Oz along the 2D production, right? And so you get some more action type movies in the bottom and more, I don't even know how to classify these movies. Being John Malkovich and the Royal Tenenbaums, they're a quite unique flavor, but those are the ones that clump up there, right? And so you could do all sorts of different types of visualizations and queries onto the data set after you've learned these latent factor models. The one that was before was sort of a more global projection. Here's one that's sort of centered around a query. In this case, it queries a movie. Okay, so just the recap of collaborative filtering. The goal is to predict every user item rating. But we only observe a small subset of the ratings, and we don't have any features. And so there exists a low-rank subspace, a k-dimensional subspace, that captures all the interesting variability in describing different users and items. And the goal is to learn that low-rank decomposition, that k-dimensional matrix factorization, such that we can impute the missing values, extract or basically fill in the missing values. And that corresponds to learning a linear model and learning the features of the linear model such that we have a linear model for every user item and item. That's the intuition. Okay, so just as an aside, so let's come back to the idea of multitask learning, which we talked about a few weeks ago, right? So suppose there are capital M tasks, right? And we want to learn a parameter matrix, like a weight matrix, to solve these M tasks. So every column, is this column? Well, okay, forget if this is column or row. Every column or row of W is the weight vector you're learning for that task, right? I guess this is row. Column. Yeah, this is column. Sorry. So every column is a parameter vector for a task indexed by little m, and we're solving, in this case, linear regression, right? So we have m such training sets, and we assume that these training sets are going to be related. We further assume, for simplicity, although you don't need this in practice, that you get the same feature vector, right? The same input feature vector for every data point. So every data point in each of the training sets has you can couple their feature vectors together. The one entry has this exact same feature vector. They have a slightly different y, right? And the goal is to learn, solve this regression problem, right? So how might one regularize, right? So R here's the regularizer. Right? So if we use the standard squared L2 norm, right? So just the square of W, right? Then this simply is the sum of the entries of W, sum of the squares of the entries of W. So this actually decomposes completely into M separate learning tasks, right? And so this decomposes to independent tasks, right? And for every task, we'll learn D parameters if each of these vectors has length D, right? And that's not very interesting. It's just like solving every problem independently. We're not actually sharing data across the different learning tasks if we assume that there's some useful information between them, right? Okay, here's an alternative. Let's regularize the trace norm of W, right? So now we assume that the whole parameter matrix has low rank, right? Which means that the variability of the weight vectors must lie on some low-dimensional subspace within the full space, right? Just to recall that we have this equivalence here, right? Where the trace norm is equal to finding a UV matrix decomposition UV transpose with minimum squared norm on U and V, Frobenius squared norm on U and V. So we could equivalently, under some conditions, equivalently rewrite that problem that we had before into this, right? Where now we learn so if U and V have dimension k, so the ambient dimension of x is d. If each column vector of U has dimension k, and V projects x from d dimensions to k dimensions, right? So what we're doing is we're learning a projection of x, the original feature vector, onto a k-dimensional subspace, right? And then we're learning a k-dimensional linear model per user. And so we've reduced the learning problem from learning a d-dimensional model per user to learning a k-dimensional model per user, per task, and then learning a single projection of data points onto a k-dimensional representation that is going to be used across all tasks. So whereas the number of parameters before is capital N by D, number of parameters here is D by K plus N by K, which can be much smaller than N by D, if K is much smaller than D. Any questions on that? So in the case where x is an indicator vector, right? So it's 1 in a single element and 0 in all the other elements. This is exactly the collaborative filtering problem, right? Because then x would simply activate a a single row or column, sorry, of V, and it wouldn't look at any of the other ones. So in the case where X is just an indicator vector, this is exactly the collaborative filtering problem. And so this is a good assumption to make if the low rank assumption is a good assumption, right? So, if the variability of the parameters of the model parameters across these n tasks lie in some k-dimensional subspace of the full d-dimensional space, if that assumption is a good assumption, then this will help you learn those models with far fewer data per training task. This is just the summary of what I described before. And then here is an explicit reduction to collaborative filtering. If we assume that the x's are indicator vectors, right, then we just get this. And it reduces to collaborative filtering. So what I just described is actually a generalization of collaborative filter, or latent factor models for collaborative filtering. Yeah, I think I've already said everything on this slide. Are there any questions on this? Yeah.
So with these methods, it's the models that we get out U and V, they're not necessarily easy to visualize what they mean, are they?
Not necessarily, no.
Okay.
I mean, the hope is that at least some aspects of them are, but not necessarily. Yeah. We'll actually look on that very specific problem in a specific way in the second half of this lecture. And in general, we don't need just X features on X. We could have features on users, Z, right? So we have features that describe every user, every task, right? Like their geographic location, their age, gender, browsing history, etc. Then we can learn this is the most general form of learning what's called a bilinear model, a low-rank bilinear model. And in the case where Z is an indicator vector and X is also an indicator vector, this reduces to the collaborative filtering problem. So this is just a recap of what I talked about before, right? In all these cases, in all these bilinear models, the number of models that were used, the number of parameters we're learning is linear in M and N, or M and D, rather than learning the full model, which requires M times D parameters, right? So if K is, let's say, 10, and both M and D are in the thousands or millions, this is a huge savings in the number of parameters you need to estimate compared to learning the full matrix. Okay, so that's the story so far. Latent factor models reduces to this. So it's motivated by the singular value decomposition of the matrix Y, right? Where in that case you have no missing values, but we want to also be able to deal with the case where there's missing values. So we use this formulation. In the general case where we have arbitrary features, X and Z describing users and items or whatever the rows and columns semantically mean, then it projects these high-dimensional feature representations into a low-dimensional linear model, bilinear model. So to address the issue of, can we get things that are a little bit more easy to visualize, right? Let's talk about non-negative matrix factorization, unless there are any questions. Okay, so what are some limitations of PCA and SVD? Well, in a lot of cases the data is non-negative, right? And so this is true, for example, in text. This is true in lots of different domains. And if you get a data set that looks like this, right? PCA or SVD might give you the purple axes, right? And in some sense, what you actually want are the red axes, right? Like if you just eyeball this, and we'll make this a little bit more formal, of course, later. But if you just eyeball this data set, there might be like 2 axes of variation. Those are the red ones. And PCA and SVD enforces orthogonality, so they're gonna give you the purple solution. And if what we actually want to recover is the red axes, then PCA or SVD is not going to give us that. Right. So non-negative matrix factorization, the core formulation is very, very simple. You want to learn the exact same thing as in latent factor models, right? So y can have missing values. The only thing you're enforcing in this simple case is that u and v be non-negative, and you assume that y is also non-negative. That's it. So we can apply non-negative matrix factorization to CS155 eigenfaces, right? And you get, basis directions where if you unroll if you reformat the basis vector back into an image, you get sort of basis faces that look like this. Right? And this is not the nicest data set, but of course, but even here, I would argue that if you compare it to the eigenfaces we had before, where the pixel intensities correspond to both positive and negative values that we're trying to visualize, this looks a lot easier to visualize, right? Like all the coefficients are non-negative. The color intensities are exactly what they mean because the color intensities are non-negative, right? You're adding, so we're adding, so we start with a completely black image, and then we add each of these basis faces exactly as you see them according to this coefficient up here to reconstruct Michael's face, or the right coefficients to reconstruct Ola's face. So in this sense, these basis faces are much more interpretable than something that looks like this, where you have the mean face, and then we're visualizing something that corresponds to both positive and negative values. We have, what does it mean to, how do you interpret what it means to subtract this basis face, this eigenface? Right? It's much harder to visualize. Any questions on this? Yes?
So this basis is not orthogonal?
No. No, it is not. The only thing this adds is some, I guess blonde hair. Right. Yeah. Or, actually, you know what? Because we're in pixel space, it conflates blonde hair with people who have a bigger head that's I think that's true. You're also not guaranteed in this case that it's not guaranteed that the basis faces are ordered in decreasing importance, which is what you get in eigenfaces. That's not guaranteed. I guess this one corresponds to people who wear light colored shirts. Any other questions on this? Okay. So, right, as was just pointed out, the U's that we just learned, which were visualized by the basis faces, are not orthogonal to each other, right? So, how do we reverse the projection, right? So, A transpose A is not the identity, right? If A are not orthogonal. And so you typically use what's called a pseudo-inverse to if you want to do a back projection, right? And I won't go into the details. It's just something that you should be aware of. The formula is easy to look up, and this is how you reverse a projection of a non-orthogonal matrix. So the learning is fairly straightforward, right? The goal is to, you have a set of Yij's. This is a very generic formulation. You have a U and a V, and then you have a loss function that compares Yij versus U transpose V, and the U's and V's are constrained to be non-negative. That's basically it. You can add more bells and whistles. You get a bias and offset term for every for different entries. Those are all things you can add. Doesn't change the core component that we're trying to model. We do squared loss. Other people, in this case, use things like generalized relative entropy, where that looks more like the ratio of. So this one looks at the absolute distance, right, squared, and this guy cares a lot about the ratio, right? So if A, the first argument, is very large, and the second argument is very small, right? This is going to be a very, very big number, and that's bad. Right, so this cares more about the ratio, this one cares more about the Euclidean distance of the two predictions, or the prediction with the ground truth. And then you train using gradient descent. This is a differentiable function. There are faster ways of training. In certain cases, but in general, gradient descent will work. Okay, so just to sort of just do a quick side-by-side comparison, right? So SVD and PCA and the associated latent factor models, they try to find the best orthogonal bases of in this case, faces, right? The bases can be negative, right? The coefficients can be negative, often trickier to visualize. But because they're orthogonal, right, they capture more of the variability, you typically get better reconstructions with fewer bases, right? Whereas in non-negative matrix factorization, they try to find the best set of non-negative basis spaces with non-negative coefficients, right? And so where the basis spaces tend to be active, right, tend to be non-overlapping. So let me just explain what that means, right? So where this basis space tends to be active are in this parts of the feature space. If you think about the feature space as a factorization of this image, and it tends to be non-overlapping with other basis spaces, right? I mean, there's sometimes it overlaps, but they tend to be non-overlapping. Whereas if you look at eigenfaces, every part of this image has some sort of overlap with some other image, right? And that makes it messier and harder to interpret. So that's what I mean by non-overlapping, which makes it easier to visualize. Typically, that requires more basis spaces to get a good reconstruction. And then you could do a non-negative latent factor model that simply just imposes a non-negative constraint on U and V under the assumption that Y is non-negative as well. That's it. Any questions on that? So in the remaining time, I'm just going to go over a brief application of these ideas on modeling basketball gameplay using non-negative spatial latent factor models. So this is a project I did a few years ago. So we have tracking data from the NBA. Right? This is from the 2012-2013 season. How many people here like basketball? How many people here know who that is? 10%. Oh wow, it's like 10% of the class. Oh my goodness. You only retired 2 years ago. Come on. Okay, so this is Tim Duncan. He used to be a very dominant basketball player for the San Antonio Spurs. From the tracking data from the 2012-2013 season, we were able to construct this heat map of where he likes to shoot the basketball, right? And so how this heat map is constructed is we discretize the half court into 1 foot by 1 foot cells, so that's about 2,000 cells. And then we learn a weight per cell, right? And that's about 2,000 weights, exactly 2,000 weights. And that's what you get in this visualization, right? And this is a fairly good reconstruction of where Tim Duncan likes to shoot. of course, Tim Duncan is a superstar. He played in a lot of games. He played a lot of minutes. He took a lot of shots. And most players haven't played that much. We actually have a lot of missing values here, right? So how do we learn something like this for typical Joe Schmo who plays in the NBA, right? And so what we did was we basically proposed a latent factor model, right? So this is the shooting heat map, right? Of that we want to estimate. The actual model is more complicated, but this sort of illustrates the core concept that's relevant to this lecture. And we want to factorize this guy. So D is 2,000, the number of locations on the court. M is the number of players. In that season, it was 457. And we want to be able to estimate this shooting affinity matrix. And we want to do this even for players who haven't played that much, right? And so we basically made the assumption that the variability in shooting profiles is low rank. It lies on some low-dimensional projection of this space. And so we learned this player factors and location factors, right? And K here is going to be 10, right? And so then we just told this model, we made the assumption that it's rank 10. We fit it to the data of where people shot the ball. And then in this case, we're going to visualize the 10 location factors. So K equals 10, D is 2,000. After I learn this model using gradient descent, I can reverse visualize each row of this location factor matrix, and that's what you're seeing in this first row of visualizations. So you're seeing the 10 rows of L being visualized as heat maps. So the first latent factor corresponds, if you follow basketball, this will be fairly intuitive. The first latent factor corresponds to shooting the corner 3, then the wing 3, the top of the key 3, the left wing, right wing, free throw area, high post, baseline, right low post, left low post, right? And then now every player's shooting profile can simply be represented as a linear, non-negative linear combination of these 10 numbers. So now we can represent every player using 10 numbers rather than 2,000. And that's a lot easier. That's a lot more. That's a lot less statistically demanding, right? And so what I show down here is just a visualization of the reconstruction of 10 players' profiles. Each of these players has a high weight on the associated shooting archetype on top of it, right? So automatically from the data, we inferred that there are these 10 shooting archetypes, or we presupposed that there were 10 shooting archetypes, and then the data told us what those 10 shooting archetypes might look like, and then we can reconstruct players as a linear combination of these shooting archetypes. And because we made a non-negative assumption and we imposed non-negativity, you see that there's relatively low overlap in where the features are active in these 10 latent factor models. Yes?
Suppose these are symmetric, and even like the inner right and inner left are symmetric, but why is the right wing and left wing asymmetric? Why is there some breaking there?
I mean, most people are right-handed.
Okay, so that's why it's sort of splitting.
I mean, the data speaks for itself. That's my default answer. I don't actually know, right? But my default answer is that most people are right-handed. Yeah. So most people like to, go towards the right. Yeah, I mean, you see there's some artifacts here. Like even here, right? There's a little bit of mass on the top, and so it's not perfect. Yes?
Did you compare it to further data and see how good these predictions were?
Yeah, we had held out data, yeah.
Oh, I mean from future seasons.
No, we didn't do that. I mean, players change so much from season to season.
Yeah.
It's hard to say. I mean, you could try to predict the projection, the evolution of a player if you had that kind of data, right? If you had training data of the next season's behavior, then you could try to predict that on a held-out set. Right? Okay. Right. so just to go over some formalism. So this is actually the system that's collecting the data. These are 2 high-def binocular stereo tracking cameras that's now installed in every NBA stadium, and this is for the Minnesota Timberwolves screenshot. And it tracks all the players, the ball, and the referees at 25 hertz. Right. So we have a game state with coordinates of all the players and who's the ball handler. So this is in the game state X. The Y is will the ball handler shoot the ball, and we also learn other things too, other than shooting. Although I only visualize shooting at that point. And then then we just simply learn a logistic regression model for whether or not the player will shoot the ball in this particular formulation. So we learn a scoring function, we exponentiate it, and then that gives us the probability, and then we want to learn the scoring function. This is the f sub x that I told you about before that we wanted to factorize. So actually the coefficients is a coefficient matrix inside the logistic regression, and you want to factorize that coefficient matrix. Yeah, so this is just, the training data is, the player configurations, where the players are, and what happened next, did the ball handler shoot the ball or not, in this very simple case. And then here we're minimizing log loss, because we're doing logistic regression. And that's it. Right. Optimization via gradient descent. We could also do other things, like where players are likely to receive passes, right? So, if this player is currently at this location, what's the probability they'll receive a pass, right? And so you can see some players like to receive the pass as their cutting baseline. Some players like to receive the pass on the post, and so on and so forth. And then we can again do the same thing where we, reconstruct where players like to receive passes, depending as a linear combination of these location latent factors, where they like to receive passes. Where the passes tend to flow, this particular latent factor component of the latent factor model is actually player agnostic. So it's just simply, it looks at locations on the court and where does passes flow from one location to the next. So if the ball is over here, this latent factor says if the ball's over here, there's a tendency for the ball to be passed either here or here. If the ball's right here, there's a tendency for the ball to be passed to here, and so on and so forth. And so there's sort of, in this case, we looked at 12 different latent factors that describe passing patterns on the basketball court. Wait, am I confusing myself? Oh no! Sorry, this is now I am now I'm actually just. This one is actually a latent factor model that computes. This latent factor is smoothing out this location versus these two locations, but this location could be active in multiple latent factors. So like, for example, this location is active in both this latent factor and in this latent factor, right? So here, we look at a single latent factor, we average out over all the, we look at a single location, excuse me, and we average out over all the latent factors, and you get, if the ball was exactly here, average out over all the latent factors, where is it likely to be passed to? Or if you receive a pass exactly here, average out over all the latent factors, where are you likely to receive the pass from? Okay, so the very last thing I want to mention is a concept called tensor latent factor models. But any questions, sorry, any questions on this? Yes?
Have there been, I'm just curious if this, have there been applications for this particular project?
This particular project, no, but we have other research projects that have been commercially deployed in this. It's, it's always a bit of, it's a combination of, what is intellectually interesting, what is mathematically interesting, what coaches would be willing to pay for, and whether or not a software company is willing to develop the software, because this is not a usable software, right? It's just a prototype. So it's a combination of multiple factors that leads to something that's delivered to the market. so most of the stuff we work on end up not being delivered to market, although I still think they're interesting ideas, and maybe in the future they will, or be combined with something else. Yeah. Okay, so the very last thing I want to touch on is a concept called tensor latent factor models. And a tensor is simply a higher order generalization of a matrix, right? A matrix you can think of as a 2 tensor. Here I'm showing you a 3 tensor, right? So it's basically if a matrix is a 2D array, a 3 tensor is a 3D array, right? And if we have this 3 tensor of missing values, we can learn a tensor latent factor model, right? So rather than a bilinear model, we can learn a trilinear model, right? So for example, there are many applications. You could have a user, you could have an item, and then you could have a query, right? This user is issuing a query to some recommender system, and we have features about the query, right? So it's a 3-way, and the prediction is a 3-way dot product, right? And so, you don't need to restrict yourselves to 2 sets of two sets of semantically interesting concepts to learn these models. You can learn 3 tensors, 4 tensors. Well, okay, it gets statistically hard to learn higher order tensors, but people do 3 tensors all the time. All right. Okay, so that's a summary of latent factor models. We learned some low-rank model of a matrix of observations or tensor of observations. Can tolerate missing values. Can also use features like the bilinear model generalizes the collaborative filtering problem. This is widely used in industry. Latent factor models are amongst the most popular models used in industry because often case the low-rank assumption that there exists some low-dimensional projection is actually true, right, or approximately true. True enough to be useful, right? So this is one of the most popular ways of analyzing data and building models in practice. So that's it. Next week we'll look at embeddings and specifically focus on a concept called word to vec. That's it.